Hey guys. Right. Hi. Week 8. There's only 5 more weeks to go, and I'm not even, supposed to lecture in week 12. So that's 4. So yeah, we're getting pretty close to the end here. Yeah, I hope more people turn up. Well, it's only 8:04. Yeah, we'll give them a bit of time. But today I was actually thinking, what we're supposed to be talking about, according to the plan I had, is basically, sorting and searching. What we'll do is, we'll start with searching. It's very easy to do a linear search on an array. So you can fill an array and search for something. And then we can try and do, actually, before we even get to that, I want to develop this intuition about the speed gains you can get from doing things one way and another. It kind of touches upon the big O notation, a feeling for the computational complexity of algorithms. We'll see if it works. I was thinking, because Agnes, I looked at the Reddit forum, and Agnes had replied to that post I made about the temperature thing, the coffee milk temperature. Did you guys see the post? Or do you guys, read the forums at all? You don't get notifications? Okay. So, all right. So you should subscribe to the blue and red, blue subreddits, right? And if you're going to do, 2B, you should also subscribe to the green. And look at the posts that students are making, because that's the way to get participation points too, right? If someone makes a post there, they can participate by, replying to that and so on. So yeah, I think this post was, what was it? It's actually connected to the previous class. Your coffee, yes, if you want to, if your goal is to keep your coffee hot longer, then should you add the cream before, sooner or later, right? And it's actually a very interesting physics question, right? And I don't know, I think Madison is here, but Maddie is the one who watches Veritasium and Action Lab and things like that. So yeah, I think she'd enjoy this discussion if she was here. So we'll do that. Maybe we'll see if and if you guys are into that kind of thing, we could. I think you'll find it interesting because it'll kind of lay the groundwork for our motivation for searching algorithm tweaks and why we prefer one kind of search over another and things like that, because it's all got to do with computational complexity. Whether you derive it on paper or not, it's all flowing from the same intuition about complexity, the economy of CPU cycles, and so on and so forth, right? So that's basically what we were trying to get at. So, so we'll do that today, I think, and then we'll use that to segue into search. I think that would be a nice way to do that. We'll see how it works. Okay. Obviously, that is a fallback plan if you guys don't have any plans of your own, and if you say, this is what we'd like to do, then that is our first preference, okay? And then I'm happy to do that. But if nothing, I would be happy to talk about the, a CS way, a computer science way of looking at that problem. I think that's a very nice problem, actually. The more I think about it, yeah. Do you add your milk sooner to your coffee or later? If you want your coffee to stay hot longer. Let's not talk about that. Resist our temptation to talk more about that. We'll do that maybe 8:30 when everybody's here. Until then, actually, you know what? When we talk about that, hey, Hiram, you have a tablet, right? You can write.
Yeah, I do have a tablet.
Right. So maybe around that time you could share the screen with your tablet. Is that okay?
Okay. Yeah, I think I can do that.
Reasonably comfortable with writing out math symbols.
Me?
Yeah.
I mean, what kind of math symbols? Like,
suppose I say integral sign, right? Integral sign.
Oh yeah, of course. I've been doing calculus for 3 years.
No worries. Okay, cool. That's great. That's we're not try not to step into that territory, but just in case, I mean, sometimes I might mention that in passing because it'll basically just, these kinds of intuitions, I feel, as long as you, in your mind, you hooks on them from multiple domains, right? From the math domain, from the CS domain, from the economy domain, the happiness domain. So there's more hooks holding on to it, the better. And I think that, as we talk about computational complexity and see how it relates to, integrals and things like that, I'll just mention that in the passing, right? So for those of you who have, are interested in this kind of thing, right? So interested in the mathematical aspects of these things. Ultimately, that's what it is, right? Whether we explicitly say it or not, or put it down on paper, that's essentially what's driving us, right? So some law. And if you have any questions, feel free to ask. Otherwise, I'm just gonna, what I'm gonna do is I'm gonna check to see if anybody posted new questions in the forums. Okay. Happy to answer any questions you may have also. So this is week 8, by the way. I think most of you should be somewhere around week, quest 7 or quest 8. Yeah, welcome, Lay. Oh, Maddie, no, that's Madison. That's it. Yeah, she shifted around. All right. Yeah. So if you have any questions, just feel free to ask. And yeah, I don't see any new posts. So the last post I saw was from Agnes. Now, I don't think she makes it to our Tuesday classes, right? She has work on Tuesday, so maybe she'll see the video. But let's try to not cover this grant again on Thursday, right? So on Thursday, what we'll do is have you guys, right, implement a bunch of algorithms on screen, right? To pass the screen around, maybe implement linear search, binary search. All of this is eventually going to factor into your quests, right? Except you don't do the quest explicitly. So you can just set up an array and try, okay, so I'm going to do linear search. I'm going to do binary search. Now you know how to time them too, right? So you know how to time your functions. So you can actually do some more interesting questions here, time more interesting things than, passing by reference and passing by copy, right? Now we could actually write a linear search program method, right? And a binary search method working over the same array, right? And the array doesn't have to be big, maybe 1,000 elements, right? Or, something like that. And then we're going to look for a random element in there. Okay, and do the same thing with linear. And by the way, you will also get to know how the questing system works, okay? Because, so what I'll show you hopefully is how you can time these two functions in the same way, scientifically same. See, what I mean is that if I have two functions and I need to time them, and I say that, I want to know how this function behaves versus that function on a bunch of random numbers, let's say 1 million random numbers, yes? Okay, so I can generate 1 million random numbers, have time this function, generate 1 million random numbers there and time that function too, right? Maybe repeat the test like 10 times and take the average, right? So is that can I do a better way of, is there a way that we can make it more scientific, right? It's already very scientific, right? Because we've tried to control for so many things, right? But there's actually one final tweak we can make to make it even more, we can control things even more. What can we do to control? So I'm generating 1 million random numbers and feeding to algorithm A. I'm generating 1 million random numbers again and feeding to algorithm B and timing them, right? And now I can tell which one's better. Yes or no? Okay. All right. So how can I make that better? Because that's what I do in questing, right? So now you get an idea. Because once you know how I test things in questing, you'll also, by the time you're done with 2A, right, you'll get a good feel for questing itself. Because questing itself, I think, is not very, you have to get a feel for it. That's what I mean, right? So you got to get used to it. And by the time you're in 2B, yeah, I know, what was I talking about? Yeah. So you'll get a feel. You'll get a feel for how I test things in the background. And I think that is what throws a lot of people away initially who just jump into 2B because they haven't got a feel for how things are tested in the background. And they say, well, I'm supposed to be passing this quest, and I'm not passing this quest. right? No, but you're not supposed to be passing that quest because it's failing some of the obvious conditions that most people don't even test for, but the real world will test for, right? So, but you have to get used to that. And if you just landed in 2B from outside, I think that is one of the hypotheses I have, right? As I'm studying about, I'm looking at why students are, some of the students, not all, right? Some of them are really enjoying the quest also, right? The ones who did get frustrated, I'm trying to look at their code and submissions and see why they got frustrated, right? Why did they complain? And I see that many of them expect tests to succeed when they should not succeed, right? But if those tests succeed, they would be a very dangerous neurosurgeon out there, all right? Because you need to be told, you know, it's okay. You can do these fine sutures. That's fantastic, but you need to know how to get to the place in the first place, right? You can't use an axe to get to the place and then do the fine sutures there, right? So you need to know all the skills perfectly, and you can't call yourself a neurosurgeon unless you can do everything perfectly. And so that's what it is, I think, is that a lot of students get frustrated when they dive into the deep end before wading to it through the shallow end and getting used to the water first, right, before diving off the yacht. And so we'll try and get to that. And so that's how we do it, right? So one of the ways in which I test it, and you can also get used to testing your algorithms more finely. Even then, you have to repeat it like hundreds of times and take the average. But the way you reduce noise even further is by feeding it the same set of 100 million random numbers. Okay, so you're going to feed it 100 million random numbers, but make sure you also feed the same 100 million random numbers here. Now, it's okay if it's like 100 random numbers or 1,000 random numbers, right? Because you can store them somewhere and feed the same numbers over. What happens if you want to feed 100 million random numbers to algorithm A and the same 100 million random numbers to algorithm B? Right, so now we have a challenge here because we have to store 100 million random numbers, right? So even assuming that each number is just 4 bytes, right? So we're talking about 400 million bytes. That's 400 megabytes of memory just sitting there. And not to mention the access times and things like that, right? It's a pain and a mess at the very least. So, so the way to do that very nicely and cleanly is to basically just say, you know what? I'm done dealing with these individual random numbers. I'm just going to control the source. Okay, so I'll make the source spit out the random numbers I want. Okay, so then you say I'm going to control srand. So if I seed srand with a value 5, it's going to generate this sequence of 100 million random numbers. Okay, I don't have to remember all these 100 million random numbers because when I go to algorithm B, I'm going to seed srand again with the value 5. And then it's going to generate the exact same 100 million random numbers. So that is how we can exploit the fact that even though we're getting pseudo-random numbers, it allows us to test some very nice things about algorithms, right? Introduce more, inject more fine-grained control, scientific control into how we test. Otherwise also, right, even otherwise, you can test your algorithms. So I just want to make sure that you can test your algorithms even otherwise by feeding it 100 million random. It'll just take longer because there's more noise in it, right? There's more noise, so it takes longer to get to the mean. Right, and so you can control for as many irrelevant factors as possible. Then you get to the mean faster. So, so that's one of the tricks that we learned in this thing. I don't know how we got started talking about randoms and srands. When did we start talking about random and srand? How these things, how these things. The algorithms, right? You're going to write these algorithms, right? A binary search and then you can time it. And you can generate the random numbers like we said, exact same random numbers. Okay, and so all of these things you can play around with on Thursday. Okay, so make a note so that even if I forget, so you can say, hey, let's try that. Okay, so you can try these things. Right, search A, search B. One of them is going to be linear. One of them is going to be binary. Okay. And then there's also going to be overhead of sorting, because if you're going to do binary search, you got to sort. These things you'll find out, right, eventually. But we'll talk about this maybe later in class. Okay, a binary search.
I have a question. Are there any other ways of searching a list? Because I've only heard
list or an array.
An array.
I'm sorry, list or array?
Oh, an array. Sorry.
Oh yeah. So if the array, if you don't know anything about the array, if it is unsorted, right? The best you can do there, I think, right? And correct me if I'm wrong. If it is unsorted, you don't know anything about the array, you just have to keep looking until you find it. So that's linear search, right? However, if you knew something about the array, right? So the thing is, when it comes down to the implementation, computer scientists will exploit anything at their disposal, not just the fact that it's, I can apply this algorithm here. Suppose I knew this algorithm, this array only contained even numbers or something like that, right? So they can bring that to bear into their algorithm somehow. So that basically it's still going to be in linear space, but it'll cut the search time in half, right? So, and things like that. So basically what we need to do is any problem we have, is look at anything that you can bring to bear, right? Just be resourceful, right? Like kids, right? Look around, see whatever you can bring to bear on the problem, put it there, right? In the right places, and see if you can make it faster. If it works, it works, right? If it doesn't, but you know why it works. So it's not like you throw things there. And so that's the other thing I've seen in questing too. So some of the students who get frustrated with questing do what I call grinding. Okay, so I don't know if you've played some racing games or Mario even, right? So on Nintendo or some of the Xbox games, right? So some of the people are, they just have a gun and they're just running around, just shooting everywhere, right? So, and then they're just jamming. They're just, what do you call it? Grinding the button or something like that. So they're not following any strategy. This is and mashing, right? And they're gonna get killed. Right? They're gonna get killed, right? So so the right way to win these games is to have a strategy, right? And I feel even when you look at these tournaments, you see the top players who are also on these Twitch streams, right? People are not watching these streams to see how they shoot, right? They're watching these streams to see what is that guy's strategy, right? And because it's like a game, it's like a movie, right? So many people say, hey, why do you watch this movie, right? So and say games too. Why do you watch these games, right? People are looking for strategy, not for how they kick the ball and things like that. Although I'm not a sports person, I've never watched a single game in my life, right? But I think I know that's what they look for, right? Because when I watch my grandfather and some uncles watch cricket, for example, back in India, right? So they're marveling at these things and thinking about what the hell is this guy trying to do, right? And so I think that's what it is. It's like a movie, right? So you watch and say, well, what is it building up to? What is the end? What is the plot? And so arrays too, I think if you don't know anything, I think linear is the best. If it is sorted, right? If you know the array is sorted, that brings a whole new league into your inventory. Because if you know you're sorted, you can go from linear all the way, right? Because think about it, even if you knew if it was odd numbers or even numbers and things like that, you're still in linear land. Your linear land, you're cutting your search space by some factor k, right? K may be somewhere over 0, right? So you're just cutting it down. But once you know that it is, it's sorted, you've just jumped into a whole new category altogether. Because now you're not in linear land, you can actually zoom right in because you can carve out entire chunks of the array and say, I don't need to look at that entire chunk anymore. We shouldn't be talking about this now. What time is it? 8:22. Yeah, we shouldn't be talking about this now. Remind me later, right? Later on today, when we're talking about search techniques and search algorithms, right? Let's talk about this and say, and go back to what Alexandria said and say, hey, we have an array. Well, how good can we do with this array, right? What are the different ways in which we can tackle the problem, right? So talk about, first of all, linear search. Second, how we can refine linear search by bringing to bear knowledge. You can, three, take it to an entirely new level. Right, and go to right, yeah, it's even possible to do the search in constant time. Okay, under very I just thought of this, so I think it's going to be an interesting problem. Remind me. Okay, so if you know something very if you have very detailed knowledge about the domain, let's say if you know that all of the numbers have got to be less than 1 million. Okay, all the numbers have got to be less than 1 million, and you want to know if a certain number exists or not. Yeah, if you're looking for a certain number, right? If you're looking for a certain number inside a vector or something like that, and you know that all of the numbers have got to be less than 1 million or 1,000 or something like that, then I think you should be able to write a simple, trivial, funny algorithm at least, right? And that will return results in constant time. Right, not even linear time. So you don't have to search through the array. You can actually tell instantly whether the array contains that number or not. If you know that all the numbers are positive and greater than, less than 1,000 or less than 1,000,000 or something, I think. All right. So those are things we can play with, right? Maybe we'll leave that as a challenge for Thursday, right? When you guys start coding on your own, that can be a challenge, right? But come up with an algorithm, and I could, post the problem to you, right? Maybe I can take the time until Thursday to construct the problem in a nice way, right? Yeah, I shouldn't. Yeah, come up with a problem that will actually be interesting for you guys to solve. Yeah, it's essentially going to be this, but I set up the walls. Set up the walls so that you have a nice little box to play in, right? So I could say, right, all positive numbers less than 1,000,000. I don't know. Yeah, I'll think of some parameters which will make it both feasible to play within the time you have on Thursday. I'll think of that, right? So I have some time later today too. Yeah. So I'm sorry, Alexandria. We'll save your question. All right. I don't know.
Okay. Okay. Thanks.
Any other questions? Yeah. Any other questions? Fernando, welcome to class. Fernando, are you here?
Yeah, I'm here.
Okay, all right. Hey, Fernando, I think you missed the last 2 classes, right? You have to watch the videos and have to ask me or your classmates or your tutors, okay, what's going on, because these 2 weeks are really critical. Yes?
Yeah. Well.
Okay, all right. So you have to really focus, all of you, right? Even the other guys who aren't here, just let them know. Because and think about that, you only have 8, 9, 10, 11. Okay, week 12 is all finals. Nobody's going to give you classes, right? I can give you classes, but we're not supposed to give you classes or introduce new material in week 12. So yeah, and then you have holidays after that, so you can take that time to do whatever you want. But for the next 3 weeks, you got to really focus. Okay. Any other questions? Yeah. Or do you guys want to talk? 10 minutes, maybe 10 minutes. I can just blend into the background, or mute and step away. 10 minutes, and then we can start at 8:35. Hopefully, maybe someone has joined by then. More people have joined by then. Otherwise, we'll just start. Right? Hiram can take the screen, and then we can start talking about that problem with the temperature and the coffee and so on, and then diverge slowly into computer science, and something. All right. Where's my notebook? All right. Let me see if I can figure something out. Okay. All right. So do you guys want 10 minutes? I don't mind, right? If you want me to talk, or if you have a question I want to talk, you need me to talk about, answer. Yeah, save questions about the final for later. Okay. So week 12, maybe no new material. Maybe we can just talk about the final then. Okay. So if you have any other questions, I'm happy to answer. Otherwise, I can just fade into the background and then give you guys 10 minutes. I'll come back at 8:35. Is that okay? Do you guys want 10 minutes to just? You can also brainstorm things to talk today, right? I've given you the rough landscape of what is on the menu, right? This week we're just according to plan, searching and sorting. Okay. Next week we can look at stacks and pointers. Slowly start talking about pointers and like this. Okay, because by week 10 we should be playing with pointers, right? We should be creating pointers and playing with pointers. Right? And then there's one other thing that I don't know if you had a chance to play with. It's called static variables and static methods. I've left that in the modules. What we can do is going forward, if you're okay with that, we can just assume that you know about statics, and if you don't, when we use it in our methods and classes, we can take a moment to talk about that. Is that okay with you? Yeah. Let's not waste time to contrive examples to talk about just statics and things like that. All right, good. Great. Yeah, 10 minutes. All right. So just call out to me if you need, and I'll just be around. Think of things to do today and ask later. Okay. So 8:35. We'll start at 8:35. 7 minutes now. Okay. Bye.
Does anyone know how to see how many trophies we have?
It's the same website for quests/Q. And then you type in your Foothill ID in the box that it asked for.
Okay, thanks. I'll make a note. So there are tests he runs where we get trophies, but if they fail, he doesn't tell us.
Well, what do you mean?
I don't know, like, so whenever a test fails, when I put in my code, it will tell me the test fails. But does that mean I'm getting all the trophies if there's no failures?
Yeah, if there's no failures, you should be getting all the trophies.
Okay,
Yeah.
that sounds good.
Usually if you get a decimal number instead of a whole number, that means something went wrong.
Okay, thanks.
Yeah.
All right, sounds good. I have an idea for what he meant with constant time search. So if we do it next week and we get stuck, I think I can unstick us. But
Cool.
yeah. What's the maximum number of trophies you can earn?
Oh, I don't know. It might be somewhere in the syllabus. I think it's
Okay.
9. Yeah,
All right, I'll check. I thought it was 155, but I guess I was wrong. No,
Yeah.
I'm definitely wrong because I have more than that.
Oh.
Yeah. Okay, I found it. It's 195.
Hey, why is there a silence here? Okay, so you have nothing to talk about? Do you want class to start? We can start right now if you want. You know, if unless you want more time to talk, which yeah, you know, the silence seems to indicate not. Yes.
Yeah.
Okay. All right. Great. Well, Hiram, yeah, do you want to take the screen and just share a browser and maybe that? And so here's what I was thinking, right? So I think, and then someone should do a Google search or something to find out the rate at which energy is lost by radiation is proportional to the fourth power of the absolute temperature in Kelvin. The fourth power, right? So T to the 4. So where T is the absolute temperature. I think that it's proportional, some constant times T to the 4.
Yeah, yeah.
Yeah. Okay. All right. Yeah, good. All right. Good. So now, Hiram, just open up a browser. Let's play with Desmos. Okay. Did you fall asleep or something? All right. Okay. So, you know, it's just jolted into existence, right? Right there when I said Hiram. Okay. Okay. All right. So yeah, open up a browser. Hey, by the way, I
Just a
can.
browser?
Yeah. Okay. Now that's fine.
Just browser? Okay.
Yeah. Open up a browser. Let's go to Desmos. Right. One of our
Desmos. Okay.
Desmos. Do you guys use Desmos?
Yeah, I do a lot.
Right.
Like Desmos. I think this.
I'd be very surprised if anyone who's you know, done high school and hasn't used Desmos. It's so cool, isn't it? Yeah. So let's say y equals some, I don't know, just say x to the 4. X to the 4. Y equals x to the 4. No, y. Oh, it just does that. Just say y equals x to the 4. Does it do y equals x to the 4?
I mean, yeah, you can, but like,
Oh,
it depends. If you want to name your function, that's when I use the equals, and if I don't, then I just.
I see. So they just give it an anonymous name if you don't.
Yeah.
So that is the rate at which so that is the rate at which energy is lost. Now we're talking about that, and the other one. So that is x is the temperature, right? Now, if you're going to add the milk sooner, assuming that it's the same amount of time, right? So if you're going to add the milk sooner, it's going to reach a lower temperature sooner. So they're both going to start at either x or some x minus delta. Yes. Well, because once you add the milk, assuming you're not going to add so much milk that it changes the volume. So if you're only adding enough milk to, let's say, change it by 5 degrees, right? From 70 degrees to 65 degrees or something like Celsius. So that delta, that change in temperature, right? So it's, you know, the other one is going to be, the other function is going to be x minus delta to the 4. Yes? Okay, so what is the difference between the two? Well, so if you look at the total energy lost, what is the total energy lost? That is the rate at which energy is lost. This is so you have to just tell me if what I'm saying is confusing or doesn't make sense, or just correct me, or you know, give me the right direction to talk about, right? So this is the rate at which energy is lost. That is the energy lost per second. Yes. So I can go into detail if you want. Okay. So just let me know. This is the rate at which energy, and let me know if you don't agree, or if you need to correct something, just step in here. Okay. This is the rate at which energy is lost. Some constant, right? So is everybody okay with this so far? Okay. It's the same kind of argument in computer science. That's why that's why I want to make sure this is all okay, right? Rate at, so the amount of energy lost is actually equal to the area under the curve. Yes or okay? Yes or no? So it is the integral from 0 to that. So that's the amount of energy lost. Yes, yes or no? Because it is the rate of energy lost times the time. Yes. So if you just chop it up into little rectangles. Yeah, you can take the unit times and add up the heights, right? So the area. So this 5 joules per second times 1 second. 6 joules per second times 1 second, right? So it's 5 joules plus 6 joules, and so forth. That's how you find it. So 5 joules per second times 1 second is 5 joules. So you actually get 5 joules, not 5 joules per second. Yes. So now you converted the rate into the actual energy. Yes. You got to tell me, right? Because this is the reason you got to give me more feedback is because it's not directly related to computer science, right? It's not directly, it's only tangentially related. And so if it does not enhance your understanding of computer science, we should not go into this road at all, right? It's not necessary because there's other examples we can use that just come from within computer science only, right? Like searching and so on, right? We can do the log X curve and y equals X curve and see the difference and so on. But it's all the same. At the end of the day, it all comes down to economy, right? So here we want to make sure that the total amount of heat lost is as low as possible. Yes? If you want your coffee to stay hot longer, you want to minimize the amount of heat lost. Yes? Okay, so basically what you want to do is minimize the area under the curve. You got to tell me if that agrees with you or not, right? Or if you want to correct that. Okay, I'm perfectly okay if you want to correct that. That would be great, right? We can have a much better discussion also, right? But you got to tell me, and tell me if this even makes sense or if it kind of relates to what you're learning in math and physics and other places, right? So you're probably doing other courses too. This is not the only course you're doing, yes? So if you're doing math and physics, this is, I'm pretty sure in physics you'll learn that, black body radiation or whatever it is called, right? So the amount at which energy is lost is related to the fourth power of the difference, right? From absolute zero. So now, yeah, okay, thank you. Hey, Desmos lets you type that integral sign now? How does it calculate that integral? Does it use Mathematica or something? Hey, how does it do that, Hiram?
I have no idea. I think it probably just uses some numerical method.
Oh, that's cool. All right, okay, cool. So integral A to B. Yeah, so is everybody okay with this? This is the total energy lost, right? So if you want to change the energy loss profile, right? So thinking of putting your product engineer hat on, right? So if you want to change the energy loss profile, because you want to, maybe design a mug that makes the coffee keep hot longer or something like that, right? So so you want to change the energy loss profile, meaning that you want to reduce the rate at which energy is lost, right? The best way to reduce, so you can basically say at this point that instead of y equals x to the 4, another curve is y equals x minus 5 to the 4. Because once you do x, once you add milk, it's no longer x degrees, it's going to be x minus 5 degrees. Yes. Or x, yeah, we should say 5. 5 degrees is reasonable, but typically it's delta, right? So some delta, some d. Right now, so the difference between the two curves is basically the energy saved. Now, if it's positive, you know that you're actually making a gain, and you know that it's got to be positive, right? You know it's got to be positive. In fact, you can you turn this around and say that after the milk it's x, and before the milk it was x plus delta. So the difference that plus the 5 extra degrees makes, right? You added the milk and got it cooler to 65 degrees. If you didn't bring it to 65 degrees, it was still at 70, right? You can now see the amount of heat loss over the same amount of time. So if it was 70, then the integral is going to give you that area, right? If it was 65, the integral is going to give a different area. So you can take the difference between the two areas. And that is how you calculate I think so. Anyway, you can check this with a product designer or some kind of materials engineer or a scientist that specializes in this area. But this would be a CS person thinking about it, because what we try and do in computer science really, I think, you can take this more, you can develop this more if you want. Okay, we won't go into more detail. You can actually have two curves showing in Desmos at the same time. You can, shade in one chunk and shade in the other, and you can look at the difference in the areas and all those nice things I think you can do in Desmos, or at least someone was, I've seen someone do that on a YouTube video at some point. Not in this problem, but, showing graphs and chunking things out. Does this make sense? Right? So you look at the algorithms and you say, the profile of this algorithm is that, if it starts with a data set of this size, it is, if it is, yeah, all right, you might say, going from, and here, that it's got to be, it is dependent. So, yeah, here's what I was going for. The intuition that I think would be nice to have is that the difference is delta, right? The difference in temperature is delta. and the amount of heat loss is related to the fourth power of that delta. It doesn't matter what the original, because it's, some constant plus delta, right? So that's going to be to the power 4. And the only thing that's really different is the fourth power of delta. Everything else, and that thing to say that it's really the fourth power of delta that is significant and everything else is insignificant is what we'll be trying to do repeatedly with big O notation, right? Because in big O notation, when we talk about that, we'll say this algorithm takes time that is a polynomial expressed in the number of terms, that number of data items to the power 4, right? So it's a fourth order polynomial in the number of data items that it has to process, right? Another algorithm might be a third order polynomial in the data items that it has to process. Yes, they both they're horrendous anyway, right? But still, fourth to the third is a huge improvement. And saying that it is even though the fourth power has a number of even though the third power term has a number of fourth power even though the third power expression has a number of fourth power terms which are unrelated to the number of data items. That's what I was going with, right? So basically what's going on here is the x plus delta to the 4, right? So obviously there's going to be an x to the 4 somewhere. Yes, there's going to be an x to the 4. But there's also going to be an x to the 4 in the other one, right? So x to the 4, and then that's x plus delta to the 4. So the two x to the 4s will cancel out. Yeah, we'll let's talk more about that when we do CS2B, right? We'll talk more about that when we do CS2B. It's totally irrelevant to CS2A, so don't even worry. We can start talking about search methods now if you want, right? But this is the intuition, right? What we want to do is, if the difference is the fourth power, right? Fourth power basically overrules everything. If the difference is the fourth power, I just want to bring it down as much as possible. Even if I bring it down by 5 degrees, right? If it'll lose less energy if it's lower by 5 degrees. I think you can do a calculation. Maybe Hiram or someone can do a calculation on paper and post it, right? For this value of the constant, k, it's not y equals x to the 4, right? It's y equals kx to the 4, right? So for this value of the constant, you can do a calculation and say that for a 5 degree difference, this is the amount of heat loss. If I change the temperature by 5 degrees lower sooner, this is the total amount of heat lost over 5 seconds, or 1 hour, right? And the other one, the total amount of heat lost over 1 hour. Started at 70 degrees, started at 65 degrees. 1 hour. You can do an integral, right? So you can easily do an integral. Let's not do it now. You can post it. You can share it under Agnes's post, right? You can share it. And thank you for the post, Agnes. Anyway, if you watch the video, all of this counts for extra credit too. But really, it's not related directly. It's related to CS2A, but it's not required directly in CS2A. But if you're taking the initiative to think about these things, and even if it's wrong, it's okay, right? That's the most important thing. The important thing is to try and think about these things and be vocal, right? And so I really appreciated Agnes's post and trying to look at it in a systematic way. It doesn't. One of the things I learned, I found very useful. So when I was at SRI, we had to undergo some training in product development ideas and calculi, right? So methods of developing a product idea from inception all the way to customer benefit, right? We don't say, value, all the way to value, inception to value. So it's called a value creation workshop. I think that's what it was called. A very long time ago, sometime. So there's a calculus you can follow. It's a very simple calculus you can follow to refine your idea repeatedly. Where was I going with that? Where I was going with that? But algorithms. I don't know where I was going with that. Sorry. I think anyway, all right. I don't know what I was talking about. Sorry, unless I kx to the 4, kx to and then you say that it's the difference is basically the fourth power of the difference is what matters. I don't know. And then and Agnes pushing in, and thank you. Yeah, and it's okay to be wrong and all that. Yeah, and trying to be formal, be formal about these things, right? And then trying to be formal is, I think, it's it's all right. Yeah. This is what I learned, and it was actually a surprise to me when I learned it, because I've seen it used many times in the past, but quantifying everything, is okay. It is important, even if all your numbers are totally wrong. So that is the thing that I found very surprising initially, but it was very nice and interesting, useful to me, in that it's okay. It's okay even if your theory is wrong, even if your everything is wrong, even if your numbers are totally out of whack. It's okay. But you got to get them down into numbers first, okay? And I think after noodling around for a very long time, I realized that the principal benefit of this approach comes from basically detaching yourself from your idea, because I think that's essentially what happens. Is basically when you put numbers down, then you're not wedded to that anymore. You just want to improve the numbers, right? And then you start looking for ways in which you can improve those numbers. Hang on just a sec. Hey, Peter, no. Bah. Well, he's trying to get at the acorns, and unfortunately, I got this bag of acorns on the inside of the glass. All right. So, was I? Yeah. So, getting the numbers down is the most important, and likewise, I think, right? And I think likewise, getting past the idea in our heads and putting it down to say, we're just going to be formal about this, right? And it helps us be detached about it and think about it objectively, right? And say, now that we've got it down, now that we know that our goal is to reduce temperature, and then we've tried this law and it doesn't work, maybe the specific heat is not the right thing to use. Maybe we'll use, the amount of black body radiation thing that we know, right? We'll pull that and say, we'll try that. So that becomes a whole lot easier than if you try and approach that. I think that is probably related. All of that is related together, and I think that it's okay. That's the reason I love these, public forums, is that it's we just make it okay to be wrong, right? We just make it totally okay to be wrong, because it is basically practice to be wrong, right? It's bad. Practice to be wrong is also practice to be right, right? And you got to be wrong, because if you are afraid to be wrong, you're going to be afraid all your life, right? The only way to conquer fear is to just be wrong, and don't give a shit about it. And our forums are a great way to do that, and you could be right too, right? So go ahead, chime in with this, and you can even take screenshots and post it and say, well, essentially we want to reduce the total amount of heat over n seconds. So if you want to integrate from 0 to n, right? 0 to n, integral, k to k x to the 4. I don't know, it's going to be k x to the 5 over 5, right? And 0 to n. So it's basically going to be k n to the 5 over 5, right? K n to the 5 over 5 minus k minus delta, k times n minus delta to the 5 over 5, I think, right? And then the n to the 5s will cancel anyway. So really, our term is delta to the 5. And we say, hey, so delta to the 4, delta to the 4. Oh, delta to the 5, because you have the integral, right? So you can say, well, you know what? The total heat loss is actually related to the 5th power of the temperature difference, right? The delta, right? So that's what we want to minimize. Yeah. So you can do that calculation and post. I think it'd be interesting too. I think it'd be really interesting. So I've never seen that done. Is that okay? Can we now proceed? I think this is a very useful exercise, right? Because you can bring this to bear on, do you agree or not, right? Or is it useless, right? Was this useful at all? Yeah, I don't know. I hope so, right? I hope so. If not, you should tell me, right? You should tell me, and we don't have to spend as much time on these things. Yeah. All right. So what we want to do is essentially, you can actually start coding right now. Yeah. Hiram, you can open up a window unless someone else wants to go. Hey, Fernando, do you want to take the screen? Because you never ever, as far as I remember, you've never taken in the screen and coded. You want to take the screen and code? Let's say not do objects now for now, right? We'll bring in objects later. right? We'll just do plain old C++ with arrays and searching and stuff like that. Fernando, are you here?
Yeah. Can I pass?
Are you near a computer? Can you take a computer and share your screen?
Can I pass for next time?
Not possible right now.
No, not possible right now.
No, I can't hear you, man.
No, not really.
Not really. Okay. Anybody else wants to take the screen? You and Hiram, if you want to take the screen, we'll just open up a window, start coding, develop some search algorithms. And you can do this. You can take this more, develop more of it on your own. Continue on Thursday. I can chime in whenever you want. Okay. And I'll tell you what we can try and do. Set up a couple of problems, right? Guide you if necessary. Can we do that? So far, everything okay so far? I just want to, I want to keep on constantly checking in because I don't want to lose any of you because it's if you've managed to come this far into CS2A, it would be a real pity, right? You should really continue all the way to CS2C, right? I think getting past the initial stages, just getting familiar with it is the biggest block, especially for Python programmers and other programmers, right? Because they already know many of the things about programming itself. What really is lacking is just a familiarity, right? So you know how to interact with people, but it's at the same time you need the first half an hour you go to a party, you're just going to meet someone, find out, right? So after that you're totally at home then, because as long as you know how to interact with people. So it's C++ is like that, right? It's just a stranger, but once you get to know them, it's exactly the same as anything else. So I know there's a lot of you like that, and it will be a pity if you just give up, because there's a great wealth of power hidden in C++ that you won't be able to unlock in other languages. You can really, but you'll have to use tailor-made libraries written in C++ by other people, right? You just have to link it blindly into your code and hope that it you get the best out of it. Why isn't anybody taking the screen? It says someone should take the screen, open up a online GDB or something. You just start coding, okay? Oh, you got two curves. Hey, you got a parabola? One of them is a parabola. Oh, g of x is a parabola. Anyway, no, I shouldn't be distracted like this. Okay, so you can close this. All right, so you can just go ahead. Let's open up an online GDB, and then we can start coding. I'll put in the comments, and then you can start coding. Okay, I'll put in the comments, and I'll just vanish. Okay, I'll put in the comments, I'll vanish, but I'll listen to what you guys are talking. Okay, about and coding, right? And even when you're coding, also speak out what you're coding, so that even if I'm not looking at the screen, I can hear. And you say, hey, put a for loop there, okay? And so I can hear what you're doing. Great. Why? Hey, Hiram, you should take the screen. Okay? Just take the screen.
Okay, should I just use the online GDB?
Is this a private?
Yeah, this is a private window.
Online GDB and just. All right. So yeah, put a comment saying, this is our code from class Tuesday, November 9. Oh, all right. So yeah. So we can say that in this program, we're going to try and experiment with different kinds of search techniques, primarily linear and binary. Okay. We're going to say multiple. Yeah, they don't have to be. Are they going to be all different? Let's not commit ourselves, right? So maybe they're going to be slightly similar. Just get rid of the word different. Okay, multiple search techniques. Multiple search techniques. Now we won't be. We'll write one program which will basically compare all of them. Okay, multiple search techniques, including particularly. Let's just say particularly. Okay, I didn't even know if we're going to be doing more than that. We only have what is it today and Thursday, right? Next week we'll start talking about stats and stuff. Okay, IO stream, do all the standard stuff. Now let's try, and in our main, let's just create a vector of I don't know, 100,000 random integers between 1 and 10,000. Yeah, that's what's great. And you can also srand right at the top. Oh, no. So this time you want to control the srand, right? So you want to issue a seed that you want to choose, right? Okay, all right, good. All right. So in fact, I'll show you what I do in the questing. Okay, so you'll get a much better idea, right? So semicolon there, next line, and so on and so forth.
How many? How many? Are we gonna?
Oh, I see. Randoms. You want to say let's say 100,000? Yeah, 100,000. That's 400,000 bytes, right? Less than a meg. Okay. All right. Now go into blank line there, blank line. And then so fill it in with one. Oh, first let's set a control seed. Okay. So put a comment there saying set the control seed to a number that we can we will remember. Okay. Set a control seed to a number that we can remember. Okay. That's great. All right. So now you say unsigned long seed equals. This is another way of doing exactly the same thing you've done before, right? Unsigned long seed equals time 0L, right? Time 0L, right? 0L, right? So semicolon. Right now, instead of just passing the return value of time directly to your rand, you got it, right? So anytime you call srand with that, you're going to rewind to the exact same point in the random table. Yep. So now you can generate even 100 million random numbers, right? You don't have to remember anything. You'll get the exact same sequence. Isn't that cool?
Yep.
Yeah. All right. Okay. So that's how I do it in questing anyway. Right. So for size t I equals 0, I less than. Actually change that 100,000 into a num rand. Okay. So change that into a constant and so on. Const size t. So let's do everything the nice way. So go to the first line of main. After main. Yeah. After main.
Oh my gosh.
Yeah. You take that and make that max num rands, num underscore rand, all caps. Const size t. Actually, it has to be size t. Yeah. Is everybody following? Okay. Hey, Fernando, we're not even talking about objects here. Okay. So I know that you were missing in the last 2 classes. Were you there the last week at all?
Yeah, I was.
Were there? Okay. All right. So assuming that you are not up to there with the, you haven't caught up on the lectures and objects, other people too, right? We're not doing objects today. We'll tie it into objects later, but as of now, we're not doing any objects. Okay. We're just doing regular C++. Okay.
Okay.
Regular C. Yeah, we can just assign it to a rand. Yeah, percent. Oh, you want to do a max rand also? Right. So you just say const size t max rand equals 10,000 maybe. You can do a const size t up there.
Oh my gosh.
Yeah, right there on the next line. No, they're there. After num rands, right? You can also have const size t max rand, right? Yeah, so we'll keep all numbers less than 10,000. I think so, right? I don't know because max rand maybe 32K. Who knows, right? We got to do a manual to check out. Yeah. Oh, by the way, maybe there's a system variable called max rand. What's the other one called? Rand max. Okay, so we're good. We're good. Okay. So the other one is actually called rand max. Okay, so ours is called max.
Okay.
All right. Okay. Now put a comment there saying what we're going to do is generate a. Hang on. You know what we need to do? Hey, Aaron, what we need to do really is it's very likely that any number you look for is going to be there, right? Because we have 100,000 cells in our vector. Yes, 100,000 cells, but only 10,000 numbers. So right. So it's so what we want to do is the other way around. So every number only has 1/10 of a chance of being there. So let's say 100,000 cells and our numbers should be up to 1 million, right? So then I think, but you know, I don't know if Rand is going to generate it up to 1 million. Can you do a man page right there? Okay, do you have a command line at all? Do you have a?
I have command line, but it's a lot harder to use here. Wait, let me see. I don't know how to use the command line in GDB.
Oh, I see. All right, let's do this, okay? Go up to the previous line. All right, so this is actually a question. I think we had this problem before in a previous quarter. I've forgotten, maybe even 3 or 4 quarters ago. And a student called Ryan, if I remember the name correctly, okay? Ryan, is Ryan Nathan? Ryan. Okay, so he said, is it possible to generate a random bigger than max rank, right? And there was a very interesting discussion in the blue subreddit, okay, about this. And some people said, you know, if you need a number that's twice as big as max rank, you just generate 2 random numbers, right? But as mathematicians and statisticians, we know that's not going to work, right? Because the random number is going to be uniformly distributed. Yes, it's uniform distribution, right? Every number has an equal chance of appearing. Yes or no?
Yeah.
Right? You take 2 of those randoms and add them together. What do you get?
Non-equal distributions.
You get a Gaussian, right? It starts peaking. It starts getting more and more bell-shaped, right? Even the central limit theorem, right? No matter what the distribution you take, right? It could be any damn underlying distribution. You generate many randoms from it and add them all together. They're all going to peak around the mean of the distribution. That's a central limit theorem, right? And in fact, you'll actually see this. You know, I think you can graph it out on the command line on Unix too, right? With awk or something like that. You'll see that you only need to do 3. You just need 3 uniform random numbers. Already it'll start looking like a normal curve. So you can't add multiple randoms together to get another random same distribution. So Ryan asked this very interesting question. See, already, right? So we're looking at the level of interestingness of the question some of the students have asked, right? So I think this is what he asked, right? Is it possible to generate a random number bigger than max rand without using any of this? Because, you know, you can go to the more sophisticated libraries in C++, which can even let you generate uniform, you know, nanosecond wide, so in floating point numbers too, random, right? So we're not going into that at all. So his question was, can we just use rand in class like we do before, right? But we know that rand is constrained because the maximum it's going to generate is only max rand. So his question was, can we generate a number even bigger than max rand, but still be uniform in our distribution, right? And so I was so very happy to see that question. So I offered a prize of, I think, about $150 to anyone who would have a good discussion about it. It's on our blue subreddit actually, so I should go and look for it again. I think it's very nice. So I think it was called Ryan's Random Challenge. You can actually search for it, Ryan's Random Challenge. And so let's try and do this, okay? So above main, let's do a big random number, okay? So let's do a big rand, right? So put a comment there saying big rand, generate a big random number that's also uniform, okay? So let's assume that our random is going to be, before we do that, let's just find the range of rand, okay? Just open another tab and say max rand, value of max rand. C++, what is max rand? C++, what is max?
So I found that it's
Rand max. Yeah, sorry, Alexandria?
I don't know if, okay, I'm not sure. You guys look, I found like different answers.
Is it 2 bytes or 4 bytes though? Yeah, cppreference.com, the second one. Oh, it is 32767. Okay, all right. So we'll just assume it's 32767. So which means 32767. So yeah, you can go back to our code. Okay, we'll assume it's 32767, or we'll make sure it's 32767 anyway, right? So all right. So what they're doing essentially is saying that our random numbers are only 2 bytes. Okay, 2 bytes, and even though it's 2 bytes, you can go from 0 to 64K. Yes, so 2 bytes is 16 bits. 2 to the 16 is 64K. Yes or no? 255 times 255. 255 times 255 is 65,535, I think. All right. So 64K, that's what we call 64K. So rand is going to take 2 bytes. This is going all the way back to our data representation, right? Rand will generate a 2-byte random number. Now you got to stay in step with me, okay? This is actually a very interesting and useful discussion, and it spans all the way back to our class number 1. data representation. Okay, it generates a 2-byte random number. Yes or no? Right now, because it is historical, right? Back in the day when there wasn't a concept of size t and all. It said I'm just going to return a positive number, right? I'm not going to generate. So it's only returning 0 to 32K. It's not returning that high bit, right? So it's only returning a positive number from 0 to 32K. It's returning an int, not a size t, right? It's returning an int that's a positive number. The positive number, the maximum range of a positive number in 2 bytes is 32K. Yes or no? Okay, so now because it is uniformly distributed, we can basically say that 32K is 15 bits. 15 bits, yes. Now 15 bits, 15 bits being randomly generated, each one with a probability of half. So each bit is being randomly generated. So each call to rand gives you 15 randomly generated bits. Yes. So all you have to do is call rand 2 times, and you get 30 randomly generated bits. But the trick is not to add them together, because adding them will destroy the underlying distribution, but to right shift one and combine the two. So you get a 64-bit number or a 32-bit number, a longer number with the bits slotted into place in the right places. Yes or no?
That's pretty cool.
Yes.
Yeah, so that's
I was thinking about that, but I didn't get it
all
into
you
binary.
do is take one random number, multiply that by 32K, and add the other random number. Right? Multiplying by 32K is the same as shifting it. Yeah. So that's why it's a very nice way to do this. And I was really happy to give out the 150K. Actually, I don't know if I gave out that 150K, but I would have been really happy to give it out to someone, right? But it was a very nice discussion all the same. They all got points. They all got extra credit points. They all did very well in CS2A also. But that's the kind of discussions we'll have, right? Maybe not now. CS2B. You're going to be in 2B. I'll talk to Ram and Beta about opening up the class, getting a lot more students, so that we'll have rich discussions, rich, interesting discussions, right? And I think but these are the kinds of things we come across in our classes, and it's really nice. So we can 32K. So you can say return long, rand times rand. Well, actually, we can left it. No, we'll just do rand. Yeah, all right, let's do it this way. Okay, so let's say unsigned long equals rand, unsigned long big rand equals rand, and then open. And let's also make sure it's 16 bits, right? Percent 32K, percent 30% rand max. But I don't know, rand max. Let's just say it's 32K. All right, let's just say it's 332. Well, what is 32K? I don't know. What is rand max? What is the value rand max?
It was 32,767.
32,767. All right. So let's say 32,767. All right. And then put a comment there saying that's rand max, but we just want to make sure. yeah. 32,767 is rand max, but should be rand max, but we just want to make sure. It's 16 bits. All right. And then it's uppercase rand max, right? It's uppercase rand max. All right, now what we want to do is we're going to say that the big random is going to be our big random times 32 times. So you're going to say big random equals on the line you have the cursor. No, on the next line, where you have the cursor. Yeah.
Shoot, I need to change
big random equals. No, right there is fine.
Oh, really?
Nah, it's okay. It's much smaller this way. Big rand equals. Yeah, you're going to say big rand times 32767 plus rand. Okay, so what that does is essentially takes the original random, which is now located in the least significant 16 bits, yeah, and multiplies by 32K, but the effect of multiplying by 32K is the same as left shifting by 16 bits. Yes?
Wait, don't we need to have like 30, that number plus 1?
Yeah, because it's an odd number, so it's not shifting.
Let me do this.
I think so. I don't know. I think, the corner case. Yeah. In fact, we can even be very clear about this. Say big rand left shift operator 15. So you're taking that value and left shifting it 15 bits, right? So you can basically, yeah, or you can put a comment there on the next line. The same effect can be on the next line. Yeah, on the next line, you can say the effect of multiplying by 32K can be achieved by left shifting big RAM by 15 bits. Multiplying by 16, yeah, multiplying by 32K, yeah, 32K can be achieved by left shifting by, yeah, 15, yeah, 50, 30, 16 bits, 16 bits. Oh, 15 bits, yeah. Yeah, is everybody clear on this? So we got, 15 randomly generated bits, and so now we got a 32 bit random number, which is uniformly distributed. Now, the thing is, the challenge here is to make sure that it is uniformly distributed. So what is the argument, right? How can you prove that it is uniformly distributed? So you got to prove that it's uniformly distributed. I think that's what it is. Now I remember, right? So I was off the challenge. The money was up for a person who could prove that it was uniformly distributed. Not just we got a new random, but it was actually, the distribution was also uniform. And I think one of the students, I'm trying to remember his name, Brendan maybe, I don't know, actually got very close to it, right? But he was also working and so on, and got sucked into other things. But there was a very interesting discussion about this. You can take a look at it. But I'm claiming, I could be wrong. Remember, right? I could be wrong, totally wrong. Maybe the output number is not uniform, right? Maybe you even plot it out. Generate like 100,000 randoms like this and plot it out, scatter plot, and say, hey, look at the scatter plot. It's all peaked and so on. It's not random. So you could prove me wrong. Or you could say mathematically you're wrong. Analytically you're wrong. So there's 100 million reasons you could say that I'm wrong, and that's great. That's great. Okay, so you should tell me that if I'm incorrect in my hypothesis or my claim or my conjecture, right? Conjecture saying that by doing this you will still get a uniformly distributed random number. So there's a challenge for you. Okay, so now we got our big random. Now you can get your big random and stuff it in the, so now you can take the big random and do a percent of max rand. 100,000 should work, yes? Big random should be 1 million, up to 1 million, right? Up to 1 million. So it should be 1,000 times 1,000. Max rand should be 1,000 times 1,000. Yeah, all right. So we got 100,000 numbers, and our max rand is 1,000 times 1,000. Yeah, does that work? So now a random number, another big rand, only has a 10% chance of being in that array. Yes? Okay, all right. Now I'm going to leave this in your hands. Okay, I'm going to leave this in your hands. Main, you're going to write outside of main, you're going to write a function called a bool, right? Bool, find index of, right? Find index of. Okay, and then it's going to take an unsigned long. Yeah, I think it's size t or a max rand is size t, and our what does it return? It returns a long. Actually, make big rand return an unsigned long too. Yeah. So we got an unsigned long. So unsigned long and unsigned long. Okay. All right. Great. Now this method, open the method. You're going to fill it in right later, right? You and the rest of the guys, right? So this method should return true if unsigned long target, unsigned long target. Sorry, on the previous line, space target. So this method returns true. Oh, and I'm so sorry. I'm sorry, Hiram. I'm talking this through to you in piecemeal. One more parameter. We need to pass the vector by parameter reference. The first parameter should be, or the second parameter, up to you, right? Should be find index of a target, comma, target comma, or the first parameter. The first parameter should be vector of size t, right? Let's also make that size t on line 26. Vector of vector of unsigned long. Unsigned long and size t are the same. Up to you, right? We can call it vector of unsigned long just to be in keeping with vector of unsigned, and pass it by reference. Now we're going to say vec ampersand vec. All right, right. Now return true if target is found in vec, false otherwise. Okay, Now on the next line, you can say note vec is unsorted. Note vec is unsorted. Okay, all right. So this is your challenge. Now you can copy the same thing. Now copy the same thing. The function 19 to 22. Copy the whole thing over. Yeah, one more time. Yeah, one more time. And let's change the names of these methods slightly. Find the index of and call it version 1. Find index of and call it version 1 underscore v1, and the other one should be v2. Yeah. Okay. Now let's say the second one, say it's sorted. Second one, say that is sorted. So now we've starting to approach this question that Alexandria asked before. So we're given an array. In one case, we know something about the array, and the other case, we don't know anything about the array. So how well can we do on the vector? But in both cases, we don't have the array. We don't have control over the array. We can also make them const vectors instead of just passing by reference. We say const references. Yeah.
Right.
Yeah, just put a const. So they're just being passed by const reference, so you can't change the vectors, but we don't have control, right? So we can't change it beforehand. We can't even change the vector given to us. But we do know one thing about the vector that we didn't know in the other case. And your challenge, your mission, should you choose to accept, is to basically write the two methods. One of them should be linear search, because you don't know anything about the vector. And the other one should be binary search, which we'll do later together, right? Or you can take a crack at it and we can try and fiddle with it and fix it later. And binary search may take other methods too, right? May take helper methods saying, go and find. Maybe you're going to take more methods to do that, but up to you. But those are the two calls that you're going to make from main. On main, in main, do your loop in main. Yeah, I can do it linear there. And in main, what you're going to do is, okay, ask the user for a number between 0 and 1,000,000. What is our max number? 1,000,000, right? Yeah. Okay. Now look for this number in our randoms vector using the v1 method, using the v2 method. Okay, methods, and then the our first job is number 1. The next line, number 1. Okay, number 1. Make sure that the two methods actually work. Meaning that if we look for something that's there, it actually has to say yes or no, right? So we have to make sure that it actually works. Okay, that is our first order of business, and the second order of business is going to be to time them, right? So we can do something clever like we did last class. Maybe call them many times. Maybe reduce the size of the vectors, because we want to reduce the time taken to allocate memory and things like that. So you can play with it, and then we're going to time them and say which one is faster. And then number 3 is to copy and paste into a Google spreadsheet or Excel spreadsheet, saying for the vector sizes, the search times, vector sizes, search times, average search times. Now you can see how one of them is going to be a log X curve, and the other one is going to be a linear curve. Yeah, straight line. One of them is going to fall on a straight line, right? The time taken by one method, as the vector size gets better and better, is going to go on a straight line like this, right? The second one is going to go like a log curve, right? It's going to rise like that, and then it's going to flatten out like that very quickly. So you'll see that effect. You'll see that effect, right? And the binary search, you can see the wins it will give you very early on. So that would be a good way to do this. Is this a good place for you guys to start, right? And coding with a reasonable enough idea of what needs to get done? I think we've laid the plan, right? Enough. Yeah, enough. The plan has been for. So that we continue with that confusion. I'm going to be around, obviously, right? So it's 9:23. You have more than a half hour to code, so I'm going to be around. Just call out to me if you need anything at all, right? Or need any questions answered, or have any questions. You don't need classes for this, right? We'll come back to classes next week, okay? When we start talking about other things. But for this, we just need C++, regular program. Everybody okay with this so far? Can I basically just background myself? Yeah. All right. Great. Thank you so much. It's been a great class, although I've been the only one who's mostly talked. And thank you, Hiram, And thank you for all the others who are not here today, right? For taking the screen and driving. And I know it's a really hard job, sometimes stressful. SOA, who's not here today, right? You've been very patient with me, so thank you so much. Right? All right, I'll disappear now and call me if you need.
Okay.
Okay.
So we should probably finish these methods first.
Yeah, sounds good. So that one actually is linear, not binary. Because for
Really?
binary, you need a sorted vector, and for linear, you can do unsorted.
Okay.
Yeah, sorry. Have you done quest 7 or
No.
no? Okay, got it. This is like quest 7, like exactly.
Ah, that makes sense.
Yeah.
Okay, so does anyone want to like say something, or should I just try to make it? Um,
I don't know. I feel like it's cheating since I just did this weekend.
okay, well, I mean, it's totally fine. Okay, well, whatever, we can just do it.
Okay. Does everyone know what linear sort or linear search is?
Yeah.
Okay,
Okay.
cool.
And then we need to, if vec I, come on. Okay, there we go. Is equal to target. Wait, no.
No, I thought that was okay, right?
Wait, you're right. Target return true. Return false.
All
Okay,
right,
that should work, right?
Yeah,
Yeah.
that was great.
Okay. And then the
Okay,
binary
good,
one,
good.
that one's harder.
So,
So don't we need to like pick the middle one and then we go off that?
yeah. Does
Okay,
everyone
I
know
just
what binary sort is or binary search?
binary search.
Yeah, I keep saying sort.
Yeah.
Okay, cool. Then
Yeah.
I guess we can just make that too. How should we define the midpoint though? Like just
I don't know. I
If
called
it's
it like
beginning
mid or
plus n
It-
divided by 2.
yeah, that's what I thought. Okay, so let's make a int or yeah, we can make it a size t, I guess, but like should we?
Oh,
You have to
this
make it
one.
that it's never 0.5. So,
Right.
and I don't know if size t does that, but it will.
Yeah. Okay.
Size t probably does.
Probably, yeah. I mean,
What, Wesley? I didn't hear you.
I said you have to make sure you never get midpoint equals something 0.5.
Oh,
yeah, but that's only like
Right.
doubles and floats, right?
yeah,
Right.
that's true.
Size t. Let's just go with size t, whatever.
I think I have like a low and a high index. Does that sound familiar? So
I just said beginning and end. Same thing.
yeah, beginning and end. Yeah.
That's, yeah, we can do that.
What is, and then
Yeah, I
you
guess it works.
you check like the middle between them, and then you see less than, greater than, or equal to, and then you change high or low based on what you get. Does that sound right? Or beginning and end?
And then, so we have those, right? And then our loop will be that we, wait, should we do like while, a while
Yeah,
loop? That might
I
be
think so. Yeah, I really feel like this is cheating. I just did it. Okay.
well, most of this, yeah, I probably would have done the midpoint, but yeah, this is better. Most of this is not that hard. Let's see. So we have a while loop and we want to check for, how should we do this? Like
Oh,
how should we choose which thing we're looking at for the while? While beginning not equal end or something?
yeah, I was like beginning is less than end or something, or maybe less
No,
than
of course
equal
it's,
to.
I think
I was just,
each time the size you can keep track of the size of the array, and you divide it by 2 each time because you're looking at half of whatever was before. And then, so if size of array is
I see.
2
So you could use a
times
for
0,
loop like that.
or if it's 0, then the while loop should exit.
If which
I
one?
just-
Beginning or-
I think a pretty easy way of doing it would be like, wait, we could do like a do while and then check if beginning I is equal to end I. Because at the last step, it would make them, would it? I don't know. Shoot.
I'm not sure.
Yeah.
It might be easier to write the inside
Yeah, it
than
might,
the condition.
whatever. I'm just gonna say loop. We can decide that loop later. So what we need to do in the loop is that we are going to, should we make a midpoint? Yeah, we should make a midpoint. Okay, size d midpoint point equals beginning I. Wait, I need parentheses. Beginning I plus end I divided by 2, and then we can check if target is less than vec at the midpoint, right? And then if it's true, then end I equals midpoint.
God, I hate this part.
Yeah? Oh, you just don't like it?
Yeah, binary search is so easy to
Else.
mess up.
And else if target equals vec.
Did you notice how he assumed there would be mistakes?
Yeah, he totally did.
When I
He's,
did my homework, I messed up so much.
return true. Okay.
And then another,
Else.
yeah.
Wait, I don't need that. Else. Beginning I equals midpoint. Now, I think I liked the idea of doing this a certain set amount of times, because wait, but we also need to check if the beginning I and end I are. Do we? No, we don't. Because it's always going to be setting it to a midpoint, and we're always checking if the midpoint is that midpoint.
So, okay. What's the worst that can happen?
Good question.
It looks fine. Like no index out of bounds.
Yeah, I don't think so. The worst that could happen is it gets stuck in the loop forever if we do it for too long. But I think it'll actually be fine if we use a for loop, like Wesley suggested.
Okay.
So we just need to calculate how many it can have. How many times
Oh, I remember while I used the while, but I want to see if this works.
Okay.
Yeah.
Because we don't know if there's going to be an
So
answer to this, right?
the reason I did the while loop is I did like midpoint +1 and -1, but I wanted to see if this works.
Oh, that's interesting.
I don't know. I don't remember why I did it.
Wait, is that even?
It worked. Like I tested it thoroughly and I got all the trophies.
It makes sense. I'm just trying to figure out how you would use midpoint +1.
Because like you're checking the middle, and so then you can shorten to midpoint.
Wait, that's actually a really good point though, because like if the midpoint is right next to or equal to, if beginning I and end I have nothing in between them, then your search is done, right?
Yeah.
So we can just do that. That's really good, actually. Okay, so we can just use a while beginning I +1 is not equal to Come on, come on. And I, right?
Something like that.
I hope that that works. I think it should, but like,
Yeah.
oops. Shoot, how do I do this without using Vim shortcuts? There. Um, okay. Okay, I wanna go through the logic.
Okay.
So we have our bounds, I guess, and they start at the full thing. Then we choose a midpoint at the midpoint of
Oh,
oh shoot, do we want to have,
should NI be -1 or should it be?
it might want to be -1.
I don't
Wait,
know.
or it might want to be.
This is so
Oh, you're
rough.
right. Wait,
Like,
I just realized, yeah, you have a good point. The vex size -1, right? Because otherwise it'll be one too big
yeah,
for the index. Because we
I
want
don't
the
know.
index, not the full size of the array.
Like, and you have to memorize how to do this perfectly within like 2 minutes for interviews. It's really rough.
Let's, or maybe we're just doing it like really inefficiently somehow.
No.
I'm sure there's a nice way to do this using recursion, but
Oh, yeah, there is. But
I don't want to use recursion.
I don't either. It'll be,
I'd rather stick with loops for now.
yeah.
Okay.
Okay, you were going through the logic.
Right. Okay. So we have our beginning and end index. These are the indexes. We need to minus the size because the size gives us the size, not the last index. Okay. And then we're checking to make sure that there's something in between the indexes. So like end I has to be big, more than one bigger than beginning I, because otherwise they're right next to each other and there's nothing in between them, which means since we must have set them to be, it must have gone from this to this, right? It means that we're done with our search, right? Maybe we could even do it. If we used a do while loop, it might be better.
Let
But
me
I don't,
see. What could go wrong?
I think it might be better with a do while
Okay, we can try it.
because, how do I put this? Because we're gonna have to do this at least once. Oh shoot, we need to check if, before we do this, we probably need to check if beginning and end are the target.
Oh, so vector size can be 0.
Hmm?
Vector size can be 0 if you give it an empty thing. So if we do a do while, will it
Oh,
have a problem?
vector size can be 0. No, that's a sort of big problem because wait, vector size can be 0. But I guess it makes sense. If vector size is 0, then I mean we're not going to get anything. But how can we just?
Yeah.
If it's 0, 1, or 2, there's like no point in using this search.
So true. Yeah.
So I guess we can sort of just assume that we're not using it in those cases.
Okay.
That's pretty scuffed. Okay. I guess we could probably just if instead of looking at the midpoint, we looked at beginning I and end I every time, it would catch the ones at the beginning, but it also would be less efficient in the loop.
Yeah.
So we
because-
could just check for beginning I and end I at the very beginning and say, like, if it's if beginning I.
Oh. Yeah, we can. That would fix it.
If I feel like we're just adding so many conditions though, it's a little
Yeah.
but whatever.
It was.
Beginning
I think if the while loop condition just failed, like, but this will work.
if vec beginning I equals target, return true y. If vec end I equals target, return true y. because it lags so much. Okay. So that solves it, but it's a little. So now.
Oh, wait, so that can throw an exception. The line 35 can throw an exception now.
Right, because the -1. Wait, but that's only if they put in 0,
Oh,
right?
right, we're assuming it
We're
won't get
assuming.
called. Okay.
We are assuming that this function will only be
forgot.
called when the vector's size. Oh, come on. Can't see what I'm typing. Oh, it auto-completed. Size and the vectors y. Okay. Is greater than 1. There.
Okay.
Oh, this is so sloppy. Okay. So we have our midpoint and then the beginning and the end. Between the beginning and the end. Yeah. Check to make sure that it can't. This find index name is like so weird. Like we're not
Yeah.
really finding the index.
Yeah, agreed.
Whatever.
So, okay, I don't know. We can
Target
we
is
can run it and see if
less
it's
than the midpoint. Then the end is equal to the midpoint. Because if the target's less than the midpoint, if we have our 2 sections, then we only want to keep the left section. So yeah. And then if it's more, we want to keep the right. So that's the else case. And then the else if is if the target is equal to the midpoint, to the value at the midpoint. Oh, yeah. Yeah, I think that should somewhat work.
okay.
Wait, I remember that I was thinking of something. This condition, right, I wanted to put it at the end because if it's not true here, we're going to have to do this at least. Wait, are we? No, we're not. No, we're not. Okay, so I should keep this here. Because we want it to be if it's 2, just skip all of this and return false
Oh,
if
yeah.
it wasn't these 2. And then if it's more, then open it up. See if the midpoint, if it's 3, then the midpoint has to be the one right between them, right? And so it'll return true if it's in it, and it won't if it's not.
Yes.
Okay, I think this should work somehow. Let's try it.
Sounds good.
Sort of
Linear
wanna
will
use-
work.
Linear will work. Yeah.
Yeah.
Linear will work. The tried and
we
true
should.
method
Yeah.
of lots of loops. I don't know.
Perfect.
Okay, wait. So how should we test this? Are we going to use this randoms array?
Oh, so what's rough is that the array is so big, you can't like print out the numbers before.
Yeah, exactly, right? So I'm thinking that we want to do tests on like a not random giant
can we do
thingy
it?
and just make our own little thing.
Let's do it. Yeah,
Should we use unsigned long? We probably should.
sure.
Unsigned long test. And let's make it 10 long.
Yeah.
Come on.
You read
Come
my
on.
mind.
Oh, I knew that was gonna happen.
What's
Okay.
up with like the lag?
I really don't know. Like sometimes it just decides that it doesn't want to like show what I'm doing to me for a good second or 2.
Really? Are you like
Yeah.
remoting in to anything?
No, I'm
No?
not.
Oh.
I'm just using the internet normally. So
That's weird.
yeah, who knows? Maybe it's my computer's Wi-Fi chip or something. Whatever.
Maybe. Are you using a laptop?
Yes, I am.
Oh, gotcha.
Yeah. So
you.
let's see.
Oh,
Okay, we
can
wanna
we fill
fill
it like
this.
in line? Or,
Yeah,
oh,
that's a better idea.
I don't know. Up to you.
Wait. Oh shoot. How can I forgot how we can fill
I
to fill
totally
vectors.
forgot.
Okay, wait. Vector fill in.
I think it's for that'll probably be right.
That was definitely the wrong search. C++. Oh, come on.
I couldn't hear you again. Sorry. Maybe my sound is low.
Okay. Um, I don't know if it wants us to be able to do that for some reason.
Okay, we could just fill it
Oh,
with random.
yeah, we can just fill it. We could just fill it with randoms, but we should also like probably print out those randoms before
Yeah,
we. Okay.
sounds good.
Wait, I can just copy this bit up here and then change it a bit. Okay. And that is not what we need to change. Okay. Okay. This is test. We just want little rands, and we don't want it to be max rand. We want it to be 100 or something. I don't know.
Sure.
That should work fine. And then this is not num rands. This is test.size. Okay. Okay. Now we should have a random thing.
Oh,
And
and
then
see out.
see out. How should we print this out? We could just try printing out tests and see what it does.
Sure. I bet it'll give like a memory address. But
I'm worried that it will, yeah, right?
Yeah.
Well, we'll see.
we could also print each one out in the for loop, but
Yeah, I don't want to do that.
Select your, like, yeah.
Oh, that's why.
oh,
That's why it was being weird. Oh my gosh, please let me move the zoom window out of the way. Okay. C++. Wait, do I need to use like a C++ 17 or 14 or anything, or is it just C++?
Probably just C++.
Yeah, whatever. Okay. Okay. It did not like a lot of what we
yeah.
did.
Oh, test doesn't have a size.
Oh yeah, that would do it. Let's make it. What was it, 10?
Yeah.
Yeah. Okay, let's try that again.
What?
Okay. I'm in standard. That's so strange.
Do you have to? Is there like a?
Okay, well, I'm just gonna assume that it doesn't like doing this.
Okay.
And let's try the for loop method. Size ti. Wait, I can just. Oh my gosh. Wait, he likes triple click. Why? Then we can go. What? Okay. And we're gonna say cout test I. Like that, maybe?
Sweet.
Like that?
Sure.
Okay, let's see if it works. Yay! Okay, there was an extra comma, but no one cares. Oh, do we want to resign the seed? Like reseed the randoms before we do this?
Nice.
This rand seed. Just because, so that these are like the same except not at all. Yeah, I don't know why we do that. But we are, okay. Okay, so now we have our random stuff. And now we can do our methods on it. So let's say, what number should we look for? Like, also we should probably give it a better chance of being there. So let's make it not 100, but like 20 or no, 30.
Okay.
Because we don't want to have we don't want to have a 1 in 10 chance of our thing being there. We want to see it work. Maybe even 20.
Will it be the same randoms every time since we use the same seed?
The seed is times 0L.
Oh, yeah. So it'll be different. That's a bummer.
Yeah. I mean, we could just manually seed it as something. Like right before here, we could go srand. Oh my gosh. Why?
Doesn't the list have to be sorted to use binary search?
Oh, it does. Nice call.
So why don't
Yeah,
we
yeah, but we're
do
not
it?
going to use binary search. We're just going to try linear for now.
Oh,
And then we can sort it, and then we know.
I see.
Although our sorting method will.
Oh, I
should-
think we can use built-in sort, standard sort.
I mean, I was wondering this whole time, like, there's totally a find function for vectors and lists and strings. So
Really?
I'm pretty sure. Like, I remember. Oh shoot, I remember it being there.
Yeah, find.
Right? Yeah. I know for sure that it's for strings. I don't know so much about vectors actually. Yeah, it doesn't look like there's one for vectors.
Looks like it's just a linear sort, the find method.
That makes
I
sense.
mean, linear search.
Linear search.
Yeah, why do I do that?
Okay, so we have that. Right, where are we gonna see the random? No. Okay, so now we need to call our linear search. Let's see. Cout. What was it again? Find index of v1 test. And we want to look for, say, 10. Wait, but we need something to like tell us what we're doing. 10 is fine. 10 is in the okay. Let's see if that works. Hope it does.
All right.
Oh, I forgot that it outputs 0. Oops.
Yeah.
Wait, what can we do with that? We can make a
Is there has to be like a string method.
probably.
Convert a bool to a string. Wow, I got a YouTube video. That is so unhelpful.
Okay.
There's nothing easy. Well, that's weird. Oh, a ternary operator. Okay.
I don't know.
That works.
Wait, that it doesn't like 10 for some reason. What if I put in like 3? It seems to like 3 a lot. Of course.
Wow.
The second that I put it as 3. Okay.
True. All
Oh,
right.
but I forgot to change it here. Yeah, okay, so it works.
Cool. I've actually
Yay.
got to go, guys.
Okay. Should we try to sort this stupid thing? Okay.
All right, guys. See you Thursday.
I'm no sorting. Bubble? We could do bubble. Wait, is there just a
Maybe you just use the brackets to write out the values instead of actually making another loop to sort it.
what?
Oh, I said you want to sort a vector, right?
Yeah.
So just use brackets to and
Right,
type
yeah.
in the numbers.
Yeah, that makes
That's
sense.
how it works.
So we can go up here maybe and like write out everything.
But yeah,
And let's oh, they do support that. Very nice. Okay. So maybe equals brackets. Whoops. That should be 10 values. Yep, that's 10 values. Hope that works. Yeah, that didn't work. Um,
Oh, that doesn't work.
or I don't know the syntax. Let me see. How would I ask that? Assign vector C++.
Maybe you could do something like a loop, and then each the next element is 5 more than the first element, the previous element.
That's true. We could just do that in the loop.
Yeah.
Yeah, that would work just fine. Okay, so let's get rid of this. And uncomment this. Okay. And let's just change this to be, I don't know, 2i. There we are. Done. What? Oh, that was really dumb. Oh my gosh. Yeah, not surprised 3 isn't in the vector. Let's make it 4. And that should return true. And then it's already sorted, so we can run. Pardon. Oh, I somehow deleted a parentheses. That's so sad. Okay. Okay. And then it's sorted, so
So it works.
at least I think it does so far. Now let's
Oh.
make it one that should be false,
Oh,
because we have to test, make sure that it at least can do those two. Okay, they both sort of work.
nice.
I think that's good enough for now.
Yeah. All
Do you
right.
want- okay, I will upload this.
I gotta go.
Yep.
See you.
Bye. Bye. Okay, I'm gonna stop sharing since probably no one's looking now.
Yeah, I'm here, but I do have to go.
Okay, bye.
Bye.
I'll leave too then. Goodbye.